Hello, everyone, and welcome to my YouTube channel. Today we have with us Lewis, who is one of the authors of Natural Language Processing with Transformers, one of the most awaited books of this year, I guess, and also previous year. And it took him quite a lot of time to compile everything nicely and put it into this book. He is a physicist and a machine learning engineer. He's a colleague of mine. We work at Hugging Face, and we have worked on several projects, some of the projects together. So he's a very nice guy, and today he's going to talk about putting transformer models in production environment. So it's all yours, Lewis.
Thanks, Abhishek. And yeah, I thought what we could do today is maybe just kind of cover a couple of like the basic concepts that are involved when you want to deploy transformers into production, and then look at some code that is directly from one of the chapters of this book. And maybe to get started, it's kind of nice. I was looking through some history.
I'm sorry to interrupt you, Lewis. It seems like your video is stuck. Can you restart your webcam?
Yeah,
And
yeah,
in
sure.
the meantime, I would also like to tell the audience that today 5 lucky winners will get a copy of NLP with Transformers. It's a print book, not a PDF. And for that, you have to fill a very short form with your name, email address, and country, which I will be sharing the link in some time in the YouTube chat. And at the end of the talk, you will be able to, we will announce a winner at the end of the talk. And feel free to ask any questions that you have during the presentation.
Cool. So let's try again. You know, whenever you do live demos, the demo gods are against you. So let's try this again. Okay, so now you should see the screen. And if I share the slides.
I do see the screen, yeah. I think it's working quite well now, yeah.
Now it's good?
Yeah, I hope so, yes.
Yeah, I mean, do you see plan of attack? That's the key test.
Yeah, I can see plan of attack, but I don't see you moving.
Oh, okay. Maybe that's super weird.
Yeah, now it's fine. Now it's fine.
Yeah, let's just do it like hacky way. So I'm not gonna do the screen share full screen. Let's just do it with the slides, and then I think we should be able to see it like that. Or is it super laggy?
It's a bit laggy, yes.
Okay, then if you don't mind, shall I just try coming back with a different browser? I'm not sure why it's so bad.
Let's just share the full screen in the same desktop, and I guess it should be fine. Yeah.
Okay, so am I frozen again or not?
You are presenting right now.
Okay, let's try that. I mean, if my video is frozen, it's maybe frozen for now, and then as long as you can hear me, I guess it's okay, right?
Yeah, I guess so.
Cool. So sorry for the technical difficulties. So yeah, if you think transformers in prod is hard, apparently doing a video stream is harder. So what I thought we could start with is maybe just like walking through a little bit the process of what it's like to write a book, and show a little bit of like the story or the genesis behind it. So it was like almost like a year and a half ago, me and Leandra, we were working as data scientists in different companies in Switzerland, and we had been using like the Transformers libraries in our jobs for a while. And one of the things that we thought was like, you know, there's like tons of like these really famous blog posts from JLMR, and there's this really cool annotated transformer from Sasha Rush, but there wasn't anything that was really targeted for people in industry like ourselves who wanted to apply you know, this technology to their own projects. And so probably like one of the few times in my life I've ever cold emailed one, I basically sent an email to Tom Wolfe saying, hey, you know, we're working on putting together a book, and, you know, would you or anyone in Hugging Face want to do that? And I was thinking, okay, Tom is like the busiest guy in NLP. No way we're getting a reply. And then to like, you know, my big surprise, he said, "Oh, that's cool. Do you want to have a chat?" And my reaction to that was pretty much like, "What the hell?" Tom said, "Yes, let's talk about it." And so we had a call, and then put together a proposal to a Reilly. And it's quite a process. Like, you first have to write like a kind of draft, which shows kind of like the abstract, what it's going to cover, what the impact will be. And you also have to provide some kind of draft chapters so the editors can assess it. And after that, we sort of started working on it. And I think as a first-time author, I mean, maybe you, Abhishek, have a similar experience. I thought it was going to be way faster to write than it actually was. And so at the end, when we finally got the we've gone to print today, my reaction wasn't one of, ecstasy. It was more like one of like, oh, it's finally done. I finally conquered this beast. And yeah, so this is kind of like gives you like a sort of taste of where it started and how we finished it. And what I thought I could do today is just talk about one of the chapters in particular, which is all about this idea of like, how do you optimize transformer models when you're dealing with production kind of questions. So the sort of thing that you sort of might wonder about when you're doing like any sort of machine learning, especially if you're working in industry, is that if you come from like academia, or like I did, or if you come from perhaps a sort of background that is very heavy focused on training models, then your kind of first reaction when you do your first project in your job is like, I trained my model, I got great performance, we solved the business use case, I'm basically done, right? And as soon as you tell this to your kind of like senior engineers in your team, this is more or less the reaction that I got, which is like, you've got a long way to go. And part of the reason for that is that kind of deploying machine learning models in general tends to be more complicated than deploying standard applications that one does in software engineering. And especially when it comes to transform models, there's a couple of considerations that you have to kind of factor in. So the first one is that these models, if you've ever used like scikit-learn, for example, the models that you deal with in scikit-learn most of the time are pretty small. They're like things like maybe random forests or logistic regression, which don't have tons of parameters. So they're kind of small in terms of, the amount of disk space you need, but they're also lightweight for doing inference. So you can often do, quite quick predictions using these very simple models. And as soon as you say, we need to now do something more sophisticated, maybe we need to use BERT, like, the kind of vanilla model that most people start with, you start running into a couple of kind of challenges. And so the first one is like, say, cost. And the thing is that now you need to typically deploy BERT on a machine that maybe needs to have more RAM, it needs to have maybe more disk space. And it may also need to be a GPU, because it turns out that if you're doing inference in like a batch-wise fashion, for example, maybe you've just got a lot of documents you need to process every day just once, then running on a GPU makes a lot of sense. But there's a cost, right? So then if you've got the GPU idle, then you're not using it, you have to factor that in. And then the other one, it comes down to scale. So you may have like an application where you need to make a lot of inferences like asynchronously. So you could imagine that your application, maybe you've got it like exposed in some, we've got your model embedded in some application, and that application has now a lot of interactivity with end users. And so now you need to have a way to kind of, do these kind of inferences in a distributed way, and that gets kind of tricky. And then the last one, of course, is speed. So like, if I have a chatbot or some search engine, I don't want my model to take 1 second or longer, because most people get very frustrated if it's just a few milliseconds. So these are kind of like the motivations of like why we should even optimize models in the first place. And there's kind of 3 main techniques that I'll be sort of just touching on briefly in the slides, and then we'll dive into some code. So the first one is called knowledge distillation, which is a technique that actually goes back about 10 years now, and even longer from some pre-deep learning era. where the idea was or is to basically have two models. One is a much larger teacher model, and then you have a student model, which is the actual model that you train. And the idea is to somehow communicate the knowledge that this teacher model has to the student. And this is a technique that works quite well in practice and is an effective way of kind of building smaller models in the training phase. And the other one is weight quantization, where we can basically, discretize the weights inside the trained model. And then this allows us to basically do faster computations because we're dealing with less floating point operations. And the last one I'll touch on briefly is called weight pruning, where we basically just delete weights in the network and even some neurons. And then the kind of goal here is that by having less weights, you do less computations. But as we'll see, the kind of, even though the state of the art right now is letting us kind of build very sparse models without loss in accuracy, it tends to be quite tricky to actually convert this into hardware that is useful. Are there any questions at this stage, Abhishek?
There are a few questions, but do you want to take them now or after some time?
Yeah, I think you can drop me whenever you want. I think it's kind of nice, that way I'm not just talking to myself.
Sure. I will interrupt you. So
Cool.
if you want to take, let's take one question here, which is about distributed inferences. So I think the question is, let me see if I can find it here. So the question says, very interested in distributed inferences. Do you use Spark to enhance it?
Okay, cool. That's a really interesting question. So personally, I haven't used Spark for doing distributed inference with machine learning models. Most of the time, so the question here, right, is I've got one model, and now I want to somehow expose this to sort of some asynchronous potentially situation. So the way I've usually dealt with this in the past is actually using Kubernetes, and then having basically, containers, lots of Docker containers that allow me to kind of scale horizontally, so to speak. So the idea being that if I see that my load in terms of the number of requests is increasing, then Kubernetes will let me kind of auto scale, and basically it will just turn on more containers to cover the load. But the Spark use case, I think, could be quite interesting, probably from the perspective of batch processing. I'm not sure when it comes to this kind of real time, how that works, but that's a good question.
Okay, another question that we have is, doesn't discretizing weights affect the precision of a model? How do we account for this loss in precision?
Yeah, that's a great question. So I'll actually cover that when we get to the weight quantization.
Sure, then let's move a little bit further and then we take more questions.
Awesome, great, thanks. Cool, so let's start with knowledge distillation. And so, as I was saying before, the idea here is that we've got these two models. One is called a teacher and one is called a student. And the teacher is a model that has already been trained on the task that we're interested in. So let's suppose that we're trying to do, classification of restaurant reviews. So you can see here that we've got a review, which is like the tacos were okay. And the teacher, which has been trained as a classifier for these reviews, it might say, okay, the most likely class is meh, which seems about right given this kind of review. So the idea is that you've got this teacher model, but maybe it gets great performance in whatever metric that you're interested in, say accuracy or F1 score, but it's just too big to put into production. And what I mean by too big is generally the number of parameters it has. So we could talk about okay, as you have more parameters or more layers in your neural network, you have to do basically more matrix multiplications whenever you want to do inference, because you've got to feed the data through the whole network. And there are several models where this is kind of a problem. So a good one is there's a model called Albert, which comes in different sizes, and Albert actually gets quite good performance on a lot of kind of downstream NLU tasks. But if you use the XXL model, this is more or less, impossible to deploy in a standard setting, because, it might not even fit on a single GPU. So the idea of knowledge distillation is to say, okay, we've got this teacher, which is really good. So what we're going to do is we're actually going to train a student, and we're going to change the loss term that we often use for classification. So instead of just having the cross entropy for the student, we're going to combine it with another loss term, which is called the knowledge distillation loss. So I won't show you the nitty-gritty details of what this looks like in math because it's not that interesting. But the basic idea is that we're going to have a loss term which has two pieces. It has the normal cross entropy loss and this knowledge distillation loss. And then the question is, how do we kind of communicate the information or the knowledge that the teacher has acquired on this task to the student during training? And the most common way this is done is using something called the Kullback-Leibler divergence. And this is just like a, kind of scary term that is often used. But the basic idea is that the distributions of the predictions of the models will generally be different, especially at the start of training, because the student is just kind of randomly initialized. It doesn't really know much about the task that we're interested in. And the teacher actually has some knowledge of the task. So the distribution of the predictions will typically be higher in the direction of the target class or the ground truth. And so what this KL divergence allows us to do is it allows us to compare these two distributions in a quantitative way. And that quantitative way is described by this equation here, where you basically divide the two distributions, take the log, and then multiply it by the distribution of the teacher. And this kind of gives it a weighting that allows you to basically take into account how these two distributions are different from each other. So what this does is it now tells us, okay, the distributions as we train, the student should ideally mimic the distribution of the teacher in its predictions. And that's essentially then what happens when we do backpropagation on this loss term that involves, the standard cross entropy, which is the ground truth, and then this extra term from the teacher. And that's more or less like the main magic of how it works. You don't need anything more complicated than this, and we'll see shortly what it looks like in code. It's actually just a function that we need to implement. Now the only subtlety here is that the distribution for the teacher will typically be very peaked around the target class. If we're just doing something like classification here, if the teacher is actually really good at the task, then probably all the probabilities for all the other classes will be close to zero, because it will be very good at getting the right result. And we don't want that, because if we did that, then the information that the teacher is providing to the student would be basically no different from the ground truth, which we already are computing in the cross entropy. So the trick is to take what we have here, the same setup, but we're just going to tweak the way the teacher makes predictions by introducing this concept called temperature. So if you've never heard of temperature, it's just a technical term to just describe how we can basically soften the distribution of the predictions from a model. And the way it works is on the left-hand side, you can see here, we've got basically the ground truth. So we've got this, the tacos were okay review, and the ground truth is just one value, right? It's only meh and nothing else. But the teacher will make some predictions of the distribution, and that's what we see here in the middle with this softmax, where the temperature is equal to 1. And that's just kind of like what the teacher would, let's say, predict distributed across these classes. And you can see that it's peaked around meh because the model is quite good. But if you tune this parameter called temperature, which we'll see in code shortly, it basically has the effect of kind of flattening out the predictions of the teacher. And the reason why we would like to do this, or we could experiment with this, is it then gives a different kind of signal to the student that is somehow more rich, or just augments the signal it's already getting from the ground truth. So this is the kind of basic extra concept that one needs. And with those two things, with temperature and this picture, this is basically how one can train very, very small models from very large models. And there's a couple of subtleties that one has to worry about with transformers. So for example, you typically need that the teacher and the student are the same model type. And what I mean by this is that if you take something like Roberta as your teacher and your student is like Distilbert, then you're going to actually end up with a mismatch in the way that the kind of inputs are processed, and typically the performance won't be very good. So that's just a small detail that one should be aware of. But generally speaking, if you have two models that are of the same type and one is larger than the other, then this technique will allow you to train smaller models, which are therefore faster. Any questions on knowledge?
Yeah, so there are some questions around knowledge distillation. So let's take a few of them.
Sure.
So the first question is, what is the difference between knowledge distillation and transfer learning?
Great. That's a really interesting question. So when we talk about transfer learning, we typically say that we've got a model that's been initialized with the weights of some pre-trained model. And, this would be something like, I don't know, a language model that's been trained on Wikipedia or something. And then we do fine tuning of the head, for example, of this model for the task at hand. So we're transferring from one task, which was during pre-training, to the task that we're interested here. Now, the main difference in knowledge distillation is that we're initializing the student in the same way. So the student is actually doing a form of transfer learning because it's going to be initialized with pre-trained weights from BERT, for example. But the difference is that instead of just doing normal fine-tuning or normal transfer learning, we're changing the loss function for the training so that we have this additional signal coming from this second model. And that's basically the only difference, that there's the loss term is just different for knowledge distillation. And it also means that when you do like transfer learning, you may, for example, if I wanted to do transfer learning with a very small model like TinyBERT, this is like a really, really small transformer, then what I would typically find is that the performance I get in terms of accuracy from just doing transfer learning with TinyBERT is actually worse than the performance I would get with using TinyBERT with a teacher, which is something like, BERT large. This is one of the main kind of benefits of knowledge distillation.
Okay, the next question is, why only KL divergence is used and not others?
Yeah, so KL divergence is just, let's say, the canonical or the simplest approach that is used in the literature and in practice. But of course, you can add other terms or other ways of comparing the predictions from the teacher and the student. And for example, in the Distilbert paper by my colleagues at Hugging Face, they actually had a third loss term, which they used to align basically the hidden states of the teacher and the student. So the KL divergence looks at the distributions of the logits, basically. But what they did in the Distilbert paper, which was quite interesting, is they said, these hidden state vectors we get, for every token, we can try to align them by looking at the cosine similarity of the teacher and the student for the hidden states. And they found that this actually gave like a kind of important extra boost in performance. So there's no kind of, let's say, God-given rule that you have to use KL divergence, but it's the most common way of comparing the distributions between the teacher and the student.
Great. Another question that we have here is, won't this knowledge distillation require more resources to train, since we have already built one model, which is there, plus we are building another student model?
Yep. That's a really good question. And the answer in general is yes, you will need, let's say, more training resources than you would ordinarily need if you're just doing transfer learning. So this technique is generally like most useful when you've kind of got two constraints. One is that you need like a good performing model. So something that is like almost as good as like your biggest model you can train. And two, you need the model to run fast on inference. And so when you have those two constraints, some of the techniques that we'll see shortly, quantization and pruning, they have some impact on those metrics. So knowledge distillation is probably your best bet at kind of satisfying those two things. But in practice, like the training the large model, I mean, we're not talking like training GPT-3. We're talking like training BERT large or, Roberta large or something. That's like in practice, that's what I've seen works kind of pretty well for many applications. So you don't really have to, the resources we're talking about are still single GPU generally, training. So it's not too crazy. But yeah, that's a good point.
Let's take one more question before moving to the next part. The question is how smaller the student can be. Is there a general rule for keeping, for example, 95% performance with the student learning if it is 60% smaller at minimum?
That's a really good question. The answer is that I don't know of any like heuristics or rules of thumb. Maybe they exist, but I'm not aware of them. I think from what I've seen, let's see. So I think in general there is like a kind of bound of like how small you can go, because essentially you're trying to compress, this knowledge from the teacher. So as far as I remember, like some of the smallest models I've seen actually take a transformer as a teacher and then compress it into like an LSTM student. And this seems to be like more or less the most extreme way you can go. I think Google did that recently for some edge devices they were working with. But yeah, I don't know a really good heuristic for this. I mean, maybe Abhishek knows since he's the Kaggle grandmaster.
Let's move to the next topic.
Cool. So, and I think this will become a bit clearer when we look at the code shortly. So what I want to talk about next is this other technique, just very high level, and it become more clearer when we look at the code, is this thing called weight quantization. So the basic idea here is that you've trained a model and you're happy with its performance, but you're not happy with basically the latency for the inference. And so there's a couple of different ways you can tackle this. And one of the ways is using what's called weight quantization, where you say, okay, my weights are typically some floating point number. And let's say most often they're something like, 32-bit numbers. And these numbers, they have some range, right? So it's like, 2 to the whatever, 32, or minus 2 to the 32 to 2 to the 32. So it's a very long range of values that these weights can take, these numbers can take. But it turns out if you actually look at the distribution of the weights in your network, so for example, on the right-hand side here, you can see basically this kind of normal distribution sort of around minus 0.2 to 0.1. This is from BERT in one of the layers. The idea is that you don't really need all of that information, right? You don't need all these humongous negative numbers and humongous positive numbers. So what we could do is we could just do a mapping. So basically we just transform the values that we can take into a much smaller range. And then if we use that much smaller range, we can actually do faster computations because we're doing less floating point calculations when we do matrix multiplication. And so what you can see in the left-hand side here is an example where you basically say, okay, I'm going to define some sort of minimum and maximum value that I want to map everything into. So this is what we would call Qmin and Qmax. And in this example, what you can see is essentially what's called an 8-bit integer, which can take values between 0 and 255. And then once you've defined the target range that you want to kind of compress all your numbers into, you then just have to define a way to map every single one of these numbers in that range using some function that is kind of, just basically it's called an affine transformation, but it's just basically a linear function. And then what you say is that any number that appears outside of this predefined range that I want to compress to we just throw it away, or we don't throw it away. We just clamp it so that it just lands on the maximum value. And so this has the effect of kind of compressing, like, think of like the number line. You're just compressing all of the numbers into this like much smaller interval. And if you apply this technique to the weights, then you will see what you see on the right-hand side, where you've now kind of discretized a little bit the values that they can take. So, previously you might have had something that was very dense with lots of weights, taking numbers, very close to each other. But then once you do this quantization technique, you basically have now kind of like binned them a little bit like a histogram. You just bin them into these like, much smaller intervals. So this, there are kind of like, say, 3 different ways people quantize neural networks and transformers in particular. So the most common, which is the one that we'll look at in the code, is called dynamic quantization. And that's more or less the picture that I'm showing you here. You just take your network, you do this kind of discretization technique, and then you're done. And it has the advantage that it's quite simple to implement, more or less. But it has the downside that it kind of just applies this like discretization procedure across, a certain set of layers in the neural network. And maybe you're quantizing things that are not optimally set up for like the data that you're actually dealing with. And so the other approach that people often talk about are things called like static quantization, where you actually use data as a way of like figuring out, which activations and which neurons are like the most important for the predictions. And then you basically focus on quantizing them. And then the last one, which is more elaborate and is only very recently becoming like kind of commonly available for transformers, is called quantization aware training, where you actually kind of trick your training, or during training, you basically pretend that you have discrete values, or these fixed point numbers, but you're actually dealing with floating point precision. And this is just a kind of fairly advanced technique to try and basically speed up training, because if your weights are quantized, then you can, the same way you can get faster inference, you can get faster training. So the kind of question that we saw earlier is like, okay, if I do this, then there must be some price, right? Like I don't, get a free lunch and quantize everything inside and go, cool, now my model has, 1/4 the number of parameters, so therefore it's 4 times faster. And the price you pay is often a performance hit in your accuracy. And the amount that you will get really depends on the architecture and the use case or the task. But in my experience, with like many of the kind of encoder only transformers, so things like BERT, Roberta, all the things that we use for like question answering and text classification and so on, you can quantize these models kind of like blindly, and the drop will be maybe 1 to 2, percentage points in your metric. That's been my experience. But I think it's much more tricky when we start worrying about quantization of like generative models like GPT and GPT-2, because they're, the metrics that we use are a little bit more sophisticated. So are there any questions, Abhishek, about weight quantization?
There is a question about pruning.
Cool, perfect.
But yeah, I wanted to take this discussion after the weight pruning part, but it seems the person really wants an answer. So let's take this one. So how is weight pruning different than dropout?
Cool. All right, so let me first explain what weight pruning is.
If you don't want to take this question right now, we can take some questions on quantization and come back to this one after you have talked about weight.
Yeah, let's do that. Let's talk a little bit about quantization, and then we can go to the weight pruning.
Okay, let me see. So the question is quantization kind of like normalization of weights?
I wouldn't put it in that way. So normalization of weights, right, is when we know that the distribution of our weights lies in some interval, and then we might, for example, subtract the mean of that distribution and then divide it by the standard deviation or whatever type of thing we want to do. So when we do that transformation, we're not fundamentally changing the precision of the numbers that we use, right? So all of those numbers that we calculate, like the mean and the standard deviation, they're all derived from, floating point values, typically 32 bits. When you do weight quantization, you're actually fundamentally changing the precision, really like at the level of the CPU instruction sets. You're changing the precision of the representations of the numbers. So, previously one of your weights, it might have had a value that could lie, in some range, and suddenly you've now, compressed that range to a smaller value. So, for example, maybe you can no longer represent the number, 10,000, because that number is going to be mapped to, the extreme end of this, 8-bit range. So I view quantization as a bit more of like a fairly fundamental thing that you're changing in the actual data structure, not so much in the distribution. That's an interesting question. Thanks.
Another question: does weight quantization affect the tail-end distribution of BERT models?
Yes. So in general, as you can see in this left-hand image, basically, any value that is outside this range that we want to define for the reduced precision is going to get clamped. So if your weights have very long tails, then you're going to just map all those tails into just one value, right? It's just going to get clamped. But I don't know. I haven't looked at like all of the weights of BERT, but like I've looked at, several layers and several of the different activations and so on. And I don't recall seeing any like very long tails, but if you do know of them, it'd be pretty interesting to explore, what impact that has when in the quantization.
I see few questions around quantization and reduction in terms of accuracy, performance, throughput trade-off. So I guess the answers to these questions will be similar. So let's take one of them. Which quantization approach has shown best performance throughput trade-off?
So I think the sneaky answer is it depends. It depends a little bit on the task, and it actually tends to depend also on the input data. So one of the considerations that I haven't really talked about here is that when we're looking at things like, let's say, throughput or latency, the sequence length that we feed to the model has an impact on the final results. So what I have seen generally is that up until recently, dynamic quantization was more or less like the best way, the best thing you could do, or let's say the simplest technique that you could do to get good precision, but also get the trade-off with throughput and latency. But as far as I'm aware, static quantization, where you actually now feed real data into your model during the quantization process, is more likely to be the state of the art, or let's say the best in class. So yeah, I would say dynamic is currently, let's say, the common thing, and then static quantization, which actually should be available soon in ONNX Runtime, which is something we'll look at quickly in the code. So yeah, those would be the ones. The quantization we're training is not so much about inference, but it's also something that I think has not been super easy to make work with transformers. It tends to work better with computer vision models. But yeah.
Okay. Another question. we have many questions coming in, so at some point we need to stop. So the question is, can we use quantization with the main reason of speeding up training, or is it a bad approach?
Yeah, that's a great question. So what I said before, right, is like there's quantization aware training. That's like one of these techniques, and it does speed up your training process, kind of in the same way that mixed precision training speeds up your training. But up until fairly recently, it wasn't really easy to make this work for transformers. So I think outside the domain of computer vision, it wasn't a good idea to quantize during training. But this is changing. Like, if I remember correctly, I think ONNX Runtime, which is a framework for doing this, that they've either done it now or they're about to release it, which is pretty cool. So maybe what we could do is we could just look at this pruning thing, and then we could jump into the code. And then, these questions, we can also revisit them while we're looking at the code, because it's the same kind of thing, but with more detail. What do you reckon?
Okay. Sounds good.
Cool. So the last technique I just want to mention briefly is called weight pruning. And the idea here is that in contrast to quantization, where we change the precision of the weights, in weight pruning, you actually delete them. So you basically zero them out in your model. And you can either prune like the neurons themselves. So this is like, you can see in the diagram here, you might just delete neurons in your network, or you can focus on deleting the connections between neurons. And most of the sort of techniques that people use, especially for NLP, focus more on like the deleting the connections. That's why we typically talk about weight pruning. And there's a couple of like techniques that are kind of, let's say, common in the literature. One of them is called magnitude pruning. And the idea here is that we need some criteria to decide, which weights should we throw away, right? And, you might say, why don't I just randomly delete the weights during training and then see what happens? And the downside with that is that you might accidentally delete, some of these connections that are actually quite important for the model to, solve the task at hand, basically get enough of a signal. So magnitude pruning says, I'm going to define like a threshold for the strength of my connections. And if weights fall below that threshold, then I'm going to iteratively delete the connections. So the idea is that, like, imagine I do an epoch or whatever number of steps, and then I'm going to measure all of the strengths of the connections between the neurons. And if these connections are below some threshold in absolute value, I'm just going to delete them. And that's kind of like a way of saying, okay, those connections weren't very important, so let's just get rid of them. And then you kind of repeat the process. So you say, okay, now I've got a new model that has like these kind of pruned connections. I'm going to train it again, and I'm going to play the same game. So I'm going to say, okay, train the model, and then I'm going to measure the connections and go, okay, what ones were weak, throw them away, and then you rinse and repeat. Now, the kind of problem with this approach is that although it like works in say theory, in practice, it means you have to train a lot of models, because you start off with your dense model at the left-hand side before pruning, and then you have to kind of train it multiple times. First, you have to train it to just figure out the connections and actually solve the task, and then you have to iteratively keep training and training it. So you basically train n models to actually get your final pruned result. So the way that people have started thinking about this in the context of NLP is that, in NLP, what we really do is we don't really train models from scratch. So this kind of iterative approach maybe doesn't make sense. And there's an interesting technique from my colleagues at Hugging Face called movement pruning. And the basic idea is, like, because we start with pre-trained weights, these pre-trained weights already encode some kind of knowledge or information about language. And so maybe instead of having to do this kind of let's train lots of models one after another and then delete weights, maybe we can actually define a technique which deletes the weights, but does it in a way that is, let's say, differentiable, which means that we can use backpropagation to basically learn the kind of optimal set of weights that we should keep during the fine-tuning or the transfer learning stage. And so what you can see in these diagrams are basically the sort of weight distributions. On the sort of x-axis is the values for a pre-trained model. And then you can see on the y-axis the distributions for the fine-tuned model. And as you can see, like, the difference between pre-trained and fine-tuned is not like very different, right? I mean, in the end, we're really only kind of tuning the weights really in the head of the network. And so what movement pruning does is it basically adaptively works out which part of the distribution of these weights we should delete, and then does this kind of in a sort of, per epoch fashion. So this is one of the sort of, let's say, state-of-the-art approaches to do pruning for transformers. But in that paper, what they found was that although you're able to basically delete like something like 95% of the weights of your network and basically get no drop in your accuracy, it actually doesn't help you when it comes to like inference, because the kind of hardware that we typically use nowadays doesn't really have the right kind of support for sparse matrices. So the idea is that, when we're deleting these weights, we're now getting a matrix, which is like getting, lots of zeros because we're just eliminating them. And if we represent that matrix as like a dense matrix, which just has, zeros everywhere we deleted something, then the actual computation that we do at the end of the day for inference is the same as if we had a dense, the original one, because we've still got, an n by n matrix, which has lots of zeros, but we still have to compute all of those products of the different matrices. So this technique was kind of improved just very recently, just a couple of months ago, by the same colleagues at Hugging Face and some others. And they actually found that if you take this idea of kind of adaptively pruning the network together with something called block pruning, where you basically just delete like whole like heads of the transformer, this allows you to then actually get the speed up, because you're now really eliminating like it's like brain surgery. You're cutting out chunks of the transformer. So this technique is really like fresh. So I won't be showing you the code for it yet, but I'll drop a link in the chat later to a library that you can play with. So there was a question actually about, okay, how is this different to Dropout? So it's really similar in a way, because when we do Dropout, right, we're kind of like randomly, let's say, masking parts of the network, and this gives us this kind of regularization feature. The main difference with like pruning is that one, we kind of like permanently delete the connections. So, if you do Dropout, you do this during training, but then when you do inference, you set your Dropout, to 0, you turn it off, because that's, now you want to have the full dense network. Whereas in pruning, we really do delete them permanently. And so then these connections, they're just gone forever. And I would say that's the sort of main difference, if that answers the question.
Yeah, sure. Thanks, Lewis. There is also a follow-up on this one.
Mm-hmm.
How are they compared with dropouts in performance? Are there any performance benefits?
Yeah, so in the movement pruning paper, they were able, I think from memory, to preserve almost, let's say, in squad, for example, they only saw a drop of like, I don't know, 1 to 2 points in F1 and exact match. But they were able to do that while deleting like 95% of the weights of the transformer, which is pretty huge, right? You take a model which is like, I don't know, 300 meg, and now you've eliminated almost 95%. You can't really ever eliminate the embedding layer, but at least everything after the embedding layer you can get rid of. And then in this follow-up work, which is very recent, what they showed is that you can get around a 2 to 3x speed up by combining this movement or adaptive pruning approach with this block pruning, where you just delete the heads of the transformer. And again, the amount of drop in accuracy or whatever metric you're following kind of depends on how many weights you're willing to throw away. And I'll see if I can find some plots to put in the description.
So another question that we have is pruning, distillation, quantization. These 3 things, are these for inference or training?
So the ones that I'm showing you now are a bit of a mix. So knowledge distillation is for training, with the goal of training a small model, which you can then use in production or for inference. So it's kind of like indirect optimization for inference. Quantization tends to be primarily like an inference technique. So the idea is that you already trained a model, and now you're going to do some tricks with it to make it discrete and therefore faster. And pruning is, again, typically a sort of mix, like a training procedure with the goal of training a very sparse model, which hopefully then can run much faster. There are techniques in pruning where you do it after training. You just delete, sort of like whole chunks of the network. But this tends to just basically make your model suck. And so that's more or less the sort of taxonomy that I would use.
Okay, one question is about information loss. So does weight pruning lead to information loss?
Yes, it does. So you will lose information about the task. So you will see a drop in performance in whatever metric, like accuracy. But the amount of drop is really kind of dependent on how much you prune. And in some cases, you can really prune almost all the weights, which is quite remarkable. I mean, there's something quite interesting called like the lottery ticket hypothesis, which is this like kind of conjecture that when we train deep neural networks, we're kind of like over parameterizing the problem, in the sense that we've got, all these like millions of parameters, and maybe like the actual task at hand only needs like a subset of those parameters. And so the lottery ticket hypothesis kind of suggests that, when we start off with like the initialization of our network, there could be like a sub network inside all this space of weights, which is already like, well optimized for what we, want to solve. And so the question is, how do you go from this kind of initialized model, which is like over parameterized, to the smaller, specific subset? And that's what these like pruning techniques are kind of trying to do in practice. If we had some like theory that could tell us, how do I go from my initialized model to my optimized one, we could kind of skip all of this, but no one has yet figured out, what is the mathematics that lets us, do this kind of one-shot transformation. Because at the end of the day, right, if someone says to you, give me this prune model and I want it to have 90% accuracy or whatever, you'll have to basically still do experiments. But in theory, there is like a kind of relationship from the original to the final model. And the question is, how do you learn that relationship in a way that doesn't require you to do lots of experiments? But yeah, have a look at some code.
Do you want to take more questions before diving into code?
Yeah, sure. I just should warn you that my son is going to barge in at some point, and we're going to have a pair programmer. So
sure. So the size of model decrease. So the size of model decreases, but time to inference remains in similar magnitude. Does block pruning happen before fine tuning or after each training epoch, like in vanilla pruning?
Yeah, great question. So in let's say until recently, it happened after training. But in this follow-up paper from the movement pruning one, they do it during training. Oh, wait, sorry, that's not right. No, it is, if from memory serves me correctly, it's done after. Actually, I kind of don't. I'm not gonna say something truly false. So the answer is, my hunch is it's done after, also in the follow-up work, but I need to double check. Shall we do some code? I think you're muted or not. I still can't hear you, Abhishek, but is it just me?
Okay, it's not just you. Yeah. So what I was saying is we do have many questions which were not answered, and we are short on time. So sorry about that. But I will share social media links of Lewis, and you can bug him there. Hopefully. So let's take one more question before moving into the code part. The question is, can pruning help avoid catastrophic forgetting in large language models?
That's a really interesting question. Okay, so let me first, for those who are maybe not familiar with the term, this concept of catastrophic forgetting typically refers to the idea that, let's suppose I train a model on Squad for question answering, and then, this is trained on Wikipedia, and then I ask myself, I've got some new data set, which is maybe, very different from Wikipedia, and I want to sort of adapt the Squad model to this new domain. And one problem that can happen is that if you kind of overtrain the model, you will basically lose the kind of knowledge or information that the model has about question answering. And so you'll see that your performance in accuracies or F1 score, whatever, goes up as you start training, and then suddenly just, collapses and the model just sucks. So when it comes to pruning, I'm not really sure the answer of whether that helps with catastrophic forgetting. I don't know the answer, but it's an interesting question. If I do find out, I'll look it up and then tweet it.
Cool. So do you still want to show some of the code?
Yeah, let's do that. So
okay. As you dive in the code, I would like to mention that we have more than 500 responses for the book. Unfortunately, we have only 5, so this is more difficult than getting into a good university. And yeah, from more than 30 countries. So I will be stopping responses for the form in the next 5 minutes. So you have only 5 more minutes to fill the form, and we will announce the winner in the end. Let's
Great.
move to the code.
So, I guess we're also having this laggy business again. Is that right?
Yeah, that's correct.
Sorry about this. I'm not sure why it does that. It must be a browser problem. Let me just see if I stop the share again. Okay. It caught up?
Nope.
I'm really sorry. Let me try again. Okay. Can you see that?
Yes. If you can make the font bigger, it would be better.
Sure.
But it's still very laggy.
Yeah, I'm really sorry. I don't know what's going on. It must be a weird browser problem. Don't use open source. That's my motto. Okay. This is pretty bad.
Do you want to share it the same way as before?
Yeah, I mean, I didn't do anything different. Let me see.
Maybe open it in a different browser.
Yeah, maybe I'm going to come in through Chrome, if that's okay with you. I'll be like 1 second. 5 seconds.
Sure.
Because I think it's a Firefox problem. Let me just try that, and then we see how we go. Sorry, and then you can chat to the audience.
Yeah. So till Lewis comes back, I just a reminder, his book is releasing soon. The Kindle version of the book is already available. So if you want to win a print copy of the book, then check the pinned comment and fill the form. I will be closing the form in 5 minutes. Yeah, we have more than 500 responses. And now in the next part, Lewis is going to show some code. So let's take a break for a few seconds, but we are going to be back really soon. Hey, welcome back.
Okay, let's try this now. Fingers crossed this works a bit better. I do apologize. Okay.
So one question was, will you share the presentation and the code?
Sure. Yeah. So the code is on the repository for the book. We can that's already open source, and the slides I will coordinate with you how we can, maybe we'll put them in the YouTube description or something.
Sure.
Okay.
Yeah.
How does this look?
Let's zoom in a bit.
Okay, zoom in.
Yeah.
Is that better?
Yeah, that's much better. Yeah.
Cool. And is it still laggy or not?
No, it's perfect.
Okay. So this is one of the notebooks from the chapter in the book where we talk about all these techniques. And I just want to give you a quick taste of like what does it look like when we implement knowledge distillation and quantization. So the kind of use case that we do in the chapter is we study something called intent detection, which is basically when you have like a chatbot, you're going to interact with people who are going to kind of exhibit some intent. Like, I would like to rent a car to go to Paris next week with 5 people or whatever. And so there's an intention in that text, and ideally your chatbot would be able to interpret that and then provide a response which is appropriate, like, oh, great, here's a link to some rental companies, so on and so forth. So what we did in the chapter is we basically took a model that we had trained on a data set called the Clink data set, which is for intent detection. And we just took something like BERT just as a sort of baseline. And the idea is that we're going to take this model and then just see how we can train smaller compressed versions of it for better inference or quantize it directly. So just to give you an idea of like what this model looks like, you give it something like I said, I want to rent a vehicle, and then it predicts a label. And there's like something like 51 labels or 61 labels in this data set. So it's a really large multi-class problem. And in this case, the model has correctly predicted that it should be car rental. So basically, the thing that you want to measure when you're doing this kind of questions of like performance when it comes to inference is you want to check, first of all, how did the accuracy change? So what I've got here is I've created a class which takes a pipeline from transformers, takes a data set, and then we implement some functions which basically compute the accuracy of this model on the data set. We compute the size on disk because that's a useful thing to know. And then we also time the pipeline in terms of its latency. And so then at the end, there's just this run benchmark function, which basically just executes all these functions and then gives us some metrics at the end. So I'm going to skip the dataset loading. If you're like kind of new to transformers and the datasets library, I recommend you buy the book. But basically what I'm doing is I'm just implementing a function which computes the accuracy on this dataset. And then I've got a function which is computing the size on disk. And then the last one is like, how do we compute the latency? And one of the things that you have to watch out for when you're measuring essentially any kind of like, say, latency or time-based process, especially with Python, is that typically you're going to get like different values just depending on like, which cores are being utilized and, are you watching YouTube at the same time? It will be slower, stuff like that. So what you need to do when you measure latency is you want to basically iterate over like some fixed number of runs. And then this way you can kind of, account for the kind of variation that you will see in the latency values. So this is, again, just a kind of simple function which just basically loops over 100 iterations. And what we're doing is we're just feeding this query, which is, what is the PIN number of my account? And then we compute how long that takes the pipeline to do. And this is now measuring, end to end, the pre-processing, from the tokenizer, the model inference itself, and then also the any post-processing, which isn't much. It's just extracting the argmax. But basically, that's what this function does. And once we have those kind of 3 dimensions of like how big the model is, how long it takes to run, and what the accuracy is, then we can just feed it this baseline that we have, which is just this BERT model. We feed it the test set from the data set. And you can see here that BERT base on disk is around 420 megabytes. And the average latency for this is like 54 milliseconds. And the accuracy is like 86, 87%. So this is like already, you could say, a pretty good model, right? It's like getting around 86% accuracy. And by the way, the classes are balanced, so we're not getting totally tricked here. And 54 milliseconds latency, you could say maybe for my use case, like that's okay. But if you're trying to build something like a chatbot, that's like really slow, right? That's like your users are gonna like probably quit your platform or your application because there's going to be a spinning wheel for too long. So we're going to see if we can improve particularly this latency metric. So let's look at this knowledge distillation topic. So remember when I was talking about knowledge distillation, we basically need to augment the loss term of the model. So we take the ordinary cross entropy loss that we use with the ground truth labels, and we just compare the logits of the model against the ground truth. But we also need to integrate this additional loss term, which is from the teacher and has this, KL divergence. So in transformers in the library, you can do this in like a really clean way. First, we're going to create a custom trainer. And to do that, we're going to, first of all, create a custom training arguments, which basically is going to introduce this temperature parameter I mentioned. And we're going to introduce a parameter called alpha, which is just tells us kind of how much signal do we provide to the model from the teacher. So basically, is the teacher going to be like the dominant part of the loss term, or is it going to be, half as strong as the cross entropy? It's just a parameter that we have to tune somehow. So these are the 2 things we have here. And then if you look at the distillation trainer, it's actually pretty simple. We just need to subclass the trainer. We need to define a teacher model as an attribute. And then we just override this compute loss function, and we just have to make sure that we return the outputs in the right way. But it's pretty straightforward. We just feed the inputs to the model, and this gives us the outputs from the student. We can then compute the cross entropy and the logits. And then what we can do is we can just compute the outputs and logits from the teacher by giving it the same inputs. And then we just feed these logits to the KL divergence, which in PyTorch is defined through this NN KL divergence loss. And then we just basically compute the KL divergence between these 2 quantities. And there's a bit of, annoying stuff here. Like we take the softmax of the logits and we multiply it by the temperature squared. It's just a convention that's used to normalize the result. But basically, at the end of the day, what we're doing is we're just computing this loss term, which has a contribution coming from cross entropy and a contribution coming from the knowledge distillation. And I don't know, I find this is kind of cool. This is like, I don't know what, like 20 lines of code. And with this, we can then basically train a student model by using, the BERT base as the teacher. So if you do that, first you need to like tokenize your text, and I'll kind of skip that. It's a pretty common step we need to do in NLP. But basically what I'm going to do is I'm going to use as my student a model called DistillBERT, which is already a smaller version of BERT. So it's already going to go faster. But then we're going to see if we can basically use this knowledge distillation technique to kind of give it a bit of a performance boost on the accuracy. So I tokenize my text. I define some metrics, which again are just accuracy. And then there's just a bunch of like stuff that we define for the training arguments, like, the learning rate, number of epochs, and so on. And if we train that, and I'm just going to define some configuration stuff. It's not super important. But if we basically train this model, then what we'll see is you can see, the accuracy goes up, and we start to actually get an interesting effect where the student has now actually obtained like a high accuracy, at least on this validation set, than the teacher does. And this is like one of the kind of weird quirks of knowledge distillation, where you can actually train a smaller model to be as performant, or in some cases better, than the teacher, just because it's getting this kind of optimized or this extra loss term to work with. So what I thought is kind of cool is we can then just wrap this in a pipeline, and then we can feed it into this like performance benchmark class. And now we can see that, the distilled model is a fair bit smaller. It's almost half the size of BERT. But in particular, because it's smaller, we've also got almost half the latency of BERT, which is great. And we've also suffered a very minimal drop in accuracy on the test set. And, we can plot this as some function, but if we, okay, this is interesting. Do I need to run this? Let's see. Okay, I'm going to run this and let's see what we get. Okay, so this is kind of cutting to the end of the story, but the basic idea is that blue here is the BERT baseline, and the model that I just showed you is where we basically do distillation in red. So you can see that we kind of halve the latency, but we preserve basically the performance of the original model. And the circle that here is in orange is just the normal distill BERT with normal transfer learning. And so you can see that, just doing normal transfer learning gives you worse performance than if you combine transfer learning with knowledge distillation, which you can see here. Any questions, Abhishek, at this stage, or should I carry on with some of the other techniques?
There are some questions. One question is it possible to train a knowledge distillation pipeline like the one shown here on CPU?
Yes, you could train it, but it will be very slow. In general, you can train any transform model on a CPU. Oh, actually, I should take that back. It's slow if you only have a few CPUs, but if you have like hundreds of CPUs, then you start getting into some interesting territory where, you can compete with a single GPU. But generally speaking, GPUs are the way to go when you want to train.
Another question is the student initialization always needed?
Yes, so let's think about this. Okay, so maybe the question is like, okay, why do we need to initialize a model like distill BERT with a kind of randomly initialized head? Maybe we could already work with something that has already been, partially tuned on the task. I don't know what happens in that case. That would be an interesting experiment to try out, which is like take a distill BERT model that's already trained on the task, and then what happens if you train it a bit more with knowledge distillation? Maybe it gets better. I'm not sure. Okay, so
one more question.
I have a whole section here about like finding good hyperparameters with a cool library called Optuna, but I'm going to kind of skip it. But the basic idea is that in the training parameters for the distillation, we basically have these two things that we don't know. So we have alpha, which basically tells us how much of the loss is coming from the cross entropy versus the KL divergence. And we have temperature, which, remember I told you, it kind of controls how smooth the distribution is from the teacher. And a priori, we don't know what these values are. So you can use this cool library called Optuna to find the kind of optimal ones for you. But I'm going to skip that, and you can look at it in the notebook itself. I want to kind of move now to quantization. And so in the quantization case, you can sort of see here. Oh no, what's going on? That's the problem with running my code twice. Okay, let's skip that. In the quantization case, what I want to show you is that sort of like under the hood, when you take your weights in PyTorch, you're kind of just doing like matrix multiplication, right, between your weight matrices. And you can see here, if I take my 32-bit numbers, which are like the default dense ones, for this example, I've got like 3 milliseconds. But then in PyTorch, there's a quantized module, which lets you basically do matrix multiplication with quantized weights. And you can see now that there's a dramatic improvement in just this simple example of just multiplying two matrices, because we're doing less computations basically in time. So the way you do quantization in Torch is like pretty simple. You just import this function called quantize dynamic. This is for the most common application. And when you do that, you can then basically pass your fine-tuned model. So what I'm providing here is the distilled model that we had from before. And you just need to specify which layers you want to quantize. And at the moment, like most of the, like say, supported operators inside the network are in the linear layer. So this is kind of like what you have to work with. Because ideally you would like to sort of quantize everything in the transformer, but just for now with PyTorch, we can only really quantize a select set of operators, which in this case is just the linear one. And then you specify the kind of target data type you want to quantize to. So in this case, I'm using one of these 8-bit integers. So we're going to kind of reduce the precision by 4. And then if we do that, and we run this model again, you can see that now quantization has kind of halved yet again the distilled model now into a quantized one, which takes up less space. And it's almost halved again the latency. So we've gone from like, we started off with like 54 milliseconds with BERT. We then went to something like 26 or something with the distilled version. And now we're at 14. So you can see that quantization is kind of giving us roughly like a 2x boost in latency compared to the distilled version, and almost like a, let's say, 3x boost compared to the teacher. And so if we plot that, just to show you what it looks like, the quantization is this green circle here. And so you can see that, you know, it's also managed, because we're inheriting some of this knowledge from the teacher, we've managed to outperform the teacher in accuracy, but also do so by reducing the latency by around a factor of 3. So the last sort of thing I want to show you quickly is a technique, or let's say a framework called ONNX and ONNX Runtime. So one of the problems with quantizing models, like I just did here, is that we need to load into memory first the raw model, and then we need to quantize it. So we're kind of like storing in memory like two potentially large models, and that isn't really the optimal way to go. So what we can do is there's let's say a framework called ONNX, which allows you to essentially serialize the network into a format which is framework agnostic, which means that you can take a PyTorch model and export it to ONNX, and then you can load that model in TensorFlow. And as long as, you know, the conversion is done correctly, this will work. You can also go the other way around from TensorFlow to PyTorch and so on. And there's a cool like project from Microsoft called ONNX Runtime, which basically says, I'm going to take these ONNX models and I'm going to define certain optimizations, which include quantization, but some more advanced things on top of it. And so the way you can do this in transformers is there's this convert function inside the transformers package, and you just define what framework you're working with. So here I'm working with PyTorch. You define the checkpoint that you want to optimize. You have to provide a tokenizer for some technical reasons. And then you just say where you want to save it. And this will now save a model or a file called, let's see, model.onnx. And this model now we can optimize in the same way that we were doing things like quantization. We can do this kind of trick using ONNX Runtime. Now, there's a lot of details that I'm not going to sort of dive into, but ONNX Runtime basically is built around this concept of what's called an inference session. And so the idea is that you load one of these ONNX models into an inference session, and the inference session can be run on different types of hardware. So you can take the same model, but you can run it on a CPU, on a GPU, or maybe on an edge device or whatever weird things like FPGA or whatever. And this, this inference session object basically then wraps the model in such a way that then you can pass inputs to it, and it will, compute those inputs and convert them back into, say, NumPy arrays for your predictions. So what I'm doing here is I'm creating what's called this inference session. And there are some like techniques that Microsoft suggests you do to optimize this ONNX model. And the basic idea is that this ONNX model, it's just a computational graph, basically. It's just like, a graph of computations from inputs to outputs. And in ONNX Runtime, you can actually optimize the structure of that graph by kind of combining operators together. So you don't have to, do them twice, you just do them in one go. Or you can also then apply these techniques like quantization. So this inference session, we just create it like this. And then once we have this, this ONNX model, we can then extract the logics from it by calling this run method from ONNX Runtime. And I just want to show you now the last step we need to do is we need to take this model and we kind of have to write our own version of the transformers pipeline for text classification. But it's quite easy in transformers. You just need to define a call method, and then we just get the inputs that we're going to get from the tokenizer. ONNX Runtime expects everything to be NumPy arrays, so we have to convert them to NumPy. And then finally, we just run them through this ONNX Runtime inference session to get the logits, and then we return essentially a list of dictionaries. So if we look at the final plot here somewhere, then what you'll see is this kind of green, purple dot here. So this is now really the most optimized model we did in the chapter, where we quantized it. It was already distilled, and we applied some of these additional optimizations from ONNX Runtime. And so you can see that, we've managed to reduce the latency by around a factor of 5 compared to the original model we started with, and with, no loss or inaccuracy. In fact, we got a boost from the distillation process. So I think that's probably like a good place to stop or take questions if there are any. What do you think, Abhishek?
Sure. So thanks a lot for the talk. It was really very interesting. We do have many questions, and I think many of them will go unanswered. But as I mentioned, feel free to ping Lewis on Twitter later. I hope that is fine, Lewis.
Yeah, of course. Yeah.
Yeah.
Ping me anytime.
Let's talk a little bit about your book before we end, or do you want to take some questions?
I think we can take some questions. I mean, maybe let's take one or two about, that just came in, and then we can talk a little bit about the book.
Sure. Okay, let me just scroll through the questions quickly, and if you want to pick something up, feel free.
Cool. So I think there's an interesting question here about, for productionization, what is your recommendation? Should we use Distilbert, quantization, ONNX for every step, or is there a slight accuracy drop and so on? Yeah, that's a good question. So it's kind of like, where do you start? So today we've talked about these 3 techniques, and I also introduced a 4th one, which is ONNX Runtime. So, and by the way, ONNX Runtime isn't the only framework that you can use. There's a very good one from NVIDIA called TensorRT. But the basic idea is that you need to sort of start somewhere. So generally speaking, I would say the simplest approach depends a little bit on the architecture. So if the model or the architecture has support for the ONNX export, my suggestion would be to start there. And then once you've got that ONNX model, you can optimize it using Runtime or TensorRT or whatever framework you have. And then you've kind of got like a stable thing to work with. You've got one serialized object, and then you can just play around with these different techniques, which these frameworks provide out of the box. However, not every single model is supported with ONNX export at the moment in the Transformers library. And there's some technical reasons why it doesn't just work for every model. So if your model isn't supported, you can either implement your own ONNX conversion for that. And if you go to the Transformers documentation, there's an example on how to do that. But if that's also maybe a little bit too scary, then at that point, I would say, okay, see if you can just quantize the model dynamically with PyTorch. And if you have the memory to store, the raw model and the quantized model, that would be, a kind of cheap way to kind of get like a 2 to 3x gain in your latency. So to summarize, if ONNX is supported, do that, and then use whatever, accelerator you want to use. And then after that, think about dynamic quantization. And then knowledge distillation, I think, is very interesting, but it's kind of like you're going to have to train a lot more. So maybe you don't want to invest that much on that side.
Great. So thanks a lot, Lewis, for joining us today. Can you talk a little bit about the prerequisites before reading NLP with transformers?
Yeah, sure. So, and again, thank you for inviting me. It's been really nice. People don't really know this, but Abhishek and I, we spend almost all our time just communicating through Slack messages. So it's quite rare. Memes, Slack messages, and emojis. So it's quite rare to see each other's faces. Yeah. So the book, we kind of wrote it for ourselves, more or less 1 year in the past. So the kind of idea of the target audience are typically, say, data scientists. So if you're working in industry in a data science role, and you're, already got some familiarity with deep learning, then this book would be kind of the right level. A good example of where you should start is actually this book. So I highly recommend reading the Fast AI book from Reilly. This will give you many of the sort of, let's say, foundations that we build on in our book. And the other sort of prerequisite at a more technical level is it helps if you have some familiarity with PyTorch, because we wrote most of the book in PyTorch. We have some sections involving TensorFlow, more to show that the Transformers library is kind of interoperable, but PyTorch would be handy. And that's kind of it in that sense. We didn't want to make it, there's hardly any math, so we don't want to make it very complicated and technical in that sense. And every chapter is designed around a single application or use case. So the idea is we worked quite hard to find examples and data sets that were much closer to what we had solved ourselves in our own jobs, rather than just picking, some sort of standard academic thing and then, showing, you can find 1,000 blogs on, how to do text classification with BERT on, SST2 or, the GLUE dataset. Yeah. Any more questions, Abhishek?
No, there are questions, so don't ask me if there are any more questions. I think we need to wrap up. We are way over time, and thanks a lot for the session. It was very informative, and people loved it. I loved it. Regarding the winners, we do have 5 winners chosen randomly. We had more than 550 people in the list. So I'm just going to copy paste the names in YouTube chat, and the winners are Daniel Meyer. Okay, the YouTube chat has messed up the formatting. So the winners are Daniel Meyer, Manel Alawi, and forgive me if I'm not pronouncing your name correctly, Hector Rabago, Vrinda Prabhu, and Snehanshu De. So these are the 5 winners of the book NLP with Transformers. Um, and this book is probably going to be the Bible of natural language processing. So yeah, congratulations. And if you didn't win, don't get disappointed. And thank you, Lewis, one more time for this session. It was really informative. And
Yeah,
thanks for
thanks a
taking.
lot again for the invitation. Just for the winners, the book, the copies, I actually don't have them in my hands right now, so it's going to take a couple of weeks to come to me, and then I'll contact you to get your mailing details. So
Yeah, sure.
just bear with me. It won't come tomorrow, but it will come as soon as I get it.
Yeah, you will get an email from Lewis soon. So thank you one more time, and see you guys in the next video. Thanks, Lewis.
Thanks everyone for coming. Bye.